You know, have you ever stopped to think about how certain shapes just pop up over and over again in the world? I mean, from the arch of a bridge to a simple stream of water from a fountain, there's this hidden mathematical blueprint behind those curves. Well, today, we're going to pull back the curtain and uncover that very secret.
So let's start with a little riddle. What in the world could a perfect basketball shot possibly have in common with one of those giant satellite dishes that beams TV into your home? I mean, they seem totally different, right? But they actually share a fundamental secret design.
And the answer? It's this incredibly simple but elegant curve, the parabola. Yep, that same shape describes the path of the basketball swooshing into the net and the reflective surface of the dish. It is without a doubt one of the most important shapes in both nature and engineering.
But how do we actually describe it? How do we predict it or build with it? Well, it turns out this curve has a secret blueprint, a universal code that's written in the language of math.
And that blueprint is called the quadratic equation. Yeah, I know, it sounds a little intimidating, but trust me, it's the key that lets us understand and work with pretty much every parabola we see. So let's actually take a closer look at what it is.
So officially, they call it a polynomial equation of degree 2, which I know sounds super complicated, but let's break that down real quick. Polynomial just means it's made up of a few different parts or terms. And degree 2, that just means the highest power of x is 2, like x squared. And it always has this general form, ax squared plus bx plus c equals 0.
But here's a much easier way to think about it. Just imagine it's a recipe for a parabola. And just like a cake recipe has flour, sugar, and eggs, the quadratic equation has its own key ingredients that decide what the final curve is going to look like. So what are these ingredients? Well, they're the numbers a, b, and c. Now, a and b are what we call coefficients. They're just the numbers that hang out with our x's. A is super important. It controls if the parabola opens up or down and how wide or skinny it is. B kind of shifts the curve left or right. And C, that's our constant, and it tells us exactly where the curve hits the vertical y-axis. You change any of these three numbers, and you get a totally different parabola.
Okay, so we have a recipe. But what good is a recipe if you don't know how to use it, right? I mean, if this parabola is the path of a ball, how do we figure out exactly where it's going to land? Well, that is what solving the equation is all about.
So it turns out there are a few different ways to tackle this, and what we're looking for are called the roots. Now, roots is just a fancy word for the spots where the parabola crosses the horizontal x-axis. In our ball example, that's where it hits the ground. You can find them by factoring, completing the square, graphing, or by using the one that works every single time, the quadratic formula. But get this, before you even start solving, there's this amazing little shortcut. Think of it like a fortune teller for your equation. It can predict what kind of answers you're going to get before you do all the hard work. And this is it, the discriminant. It's just that little part from the bigger formula, b squared minus 4ac. It's so simple. If that number is positive, boom, your parabola is going to cross the x-axis in two different spots. If it's 0, it just kisses the axis at one single point. And if it's negative, the parabola never touches the x-axis at all. It's an awesome quick check. So while all those other methods are great, there is one master key, the one tool that will crack the code for any quadratic equation you throw at it, no matter how messy it looks. And this is it, the quadratic formula. This is the whole shebang. And what's so cool is that it's got everything we've been talking about, see? There are our recipe ingredients, A, B, and C. And hey, look, right there under the square root, it's our little fortune teller, the discriminant. This is the blueprint in its most powerful, usable form. All right, enough with the theory, right? Let's get our hands dirty. The absolute best way to really get this is to just do it. Let's walk through a problem together and see how this all works in practice. Okay, let's work through one together. Imagine a ball's path is described by this equation, negative x squared plus 2x plus 3 equals 0. We want to know when it hits the ground. Easy. Step 1. Identify your ingredients. A is negative 1, B is 2, and C is 3. Step 2, we could do a quick check with the discriminant if we wanted, but step 3 is the big one. We just plug those numbers into the formula. Everywhere you see an A, pop in a negative 1. Everywhere there's a B, put in a 2. And then you just do the math. It's a step-by-step process that is guaranteed to work every single time. So, why are we doing all this? I mean, why does this mathematical blueprint actually matter in the real world? Well, the answer is, it is everywhere. Literally.
I'm talking everything from calculating the path of a rocket to helping a farmer figure out the biggest possible garden they can build with a limited amount of fence. Engineers are using this stuff constantly to design amazing bridges and, yep, satellite dishes. Even business folks use it to figure out how to set prices to get the most profit. It is all over the place.
And this just brings it all together so beautifully, right? You can see how all these pieces, the definition, the ingredients, the solving methods, and all the ways we use it, they're all connected. It's one powerful idea with roots that stretch into pretty much every field of science and technology you can think of.
So here's the bottom line, the thing I really want you to take away from all this. The quadratic equation is not just some abstract problem you find in a math textbook. No way. It's a practical, super powerful tool for describing and shaping the world all around us.
So now you know how to read the blueprint for one of the most common shapes in the entire universe. And that kind of makes you wonder, right? What other hidden patterns are just out there waiting for you to find them?